So 27 questions, chapters 5, 6, and 7. There's your typical gimme question at the end, and so 26 sort of real questions. Chapter 5, work. Work equals FD. Both calculations and conceptual. The work energy theorem, work is delta E. That is, if I do work on an object, I change its energy. And then conservation of energy. That's like, our roller coaster problems, where I'm looking at the differences in gravitational and kinetic energy, and then also springs, where I look at the elastic potential energy in those springs. So that's chapter 5 in short, and we'll come back to that as you have issues with that, okay? Chapter 6 is momentum, really just two big things, impulse, our Newton's second law, really. This is that F equals delta P over delta T. And then also collisions. And in collisions, that's where we use this idea that momentum is conserved. Pi is equal to Pf. Okay, both conceptual and calculations in those. And then chapter 7, sort of basic stuff about angles, theta, omega, and alpha, some basic calculations, and then also some conceptual things about that. It'll help you to know your unit circle. It'll help you to know the definitions for what theta, omega, and alpha are. And also kinematics. Not terribly complicated questions, generally one-step questions, sometimes two steps, but generally just one-step questions to solve for either theta, omega, or alpha. Those equations are provided for you. And then also centripetal forces. Both calculating centripetal forces and just knowing what a centripetal force is. Let's see, a couple other, I'll miss this, but just sort of some details about collisions, elastic versus inelastic. Just definitions that you need to know. And then also regarding forces, you need to know conservative versus non-conservative forces. The basics of what those are, non-conservative. Basics of what they are, conservative is a field force, it conserves energy, and it's path independent. Non-conservative are contact forces, those are don't conserve energy, and they are path dependent. Okay, so that's the test, chapters 5, 6, and 7. A lot of material, but a lot of the material is easier than what we saw in previous chapters. Or not easier, because if you don't know how to do it, it's not easy, right? But less involved material than previous chapters. Okay? Questions, either about exams or topics. Yeah.
Can you go over question 26 on exam 5, 2017 exam 2? It's like a work question.
Okay, so this was just calculating the work. And here our work is equal to FD cosine theta. That's on your equation sheet, by the way. And with these, it's always the angle that you'll use. So the angle that's given is the angle that's the cosine theta. It's not like what we had with inclined planes where you have to take 90 minus. And so it's going to be the force, which is 30 newtons, times the distance, which is 5 meters, times the cosine of 30. Cosine of 60, rather. Is that 75? Is that the answer? Yeah. Because cosine 60 is a half. Half of 150. Okay? You could see one like that. You'll certainly see one where you have to calculate the work. I don't know if you'll see one where it's at an angle or not, but you need to know that. It's on the equation sheet. All right, what else? Yeah, Rachel? Sure. Christian, did you have a particular question? Or is it related to roller coasters or springs? Huh?
Momentum.
Okay, we'll come back to you then, okay?
Oh, yes. Question one.
Okay, let me answer Rachel's question then. Or is that roller coasters or springs? No, okay. It might be hard for me to pull up that question. I'll see what I can do. Okay, Rachel, I'm going to pull up this fall 16. So here is a good question number 2. And it might not be a roller coaster, but it'll be a similar situation where I have an object that's changing height and changing velocities. And so here I want to know what is the height at point E. And I'm told in the problem that it comes to rest. So over here that V is equal to 0. And so then I want to ask myself, what kinds of energy do I have in this situation? Well, over here I have potential energy because I'm at a certain height. That's equal to mgh. But I also have kinetic energy because I'm traveling at a certain speed. Because it's moving, it has kinetic energy. Over here, I only have potential energy. And I set those equal to one another. I say the kinetic energy, that's 1/2 m times the velocity, which is 4 meters per second squared, plus m times g times h, which is 10 meters, is equal to m times g times h, which is this h over here. And then I solve for h. Our m's cancel, and I get 8 plus 100 divided by g, which is 10. That's going to equal 8. That's 10.8 or 11 meters. All of your problems like that are going to be very similar, where I have a certain situation where I have a known amount of energy, and then a second situation, your final situation, where I have an unknown quantity, the velocity or the height. Okay? That's a good example of the gravitational potential energy. Look, number 5 is similar here. In this case, I have a spring-loaded gun. And these work very similarly. Spring-loaded gun, it tells me that I've compressed it by this amount, that's my spring constant. And I want to know the speed. So this ball shoots away at a certain speed over here, where all of the elastic potential energy is now converted into kinetic energy. And so that's sort of the hard part with these problems, is just identifying what are the types of energy involved. And then I say the initial energy, which is all elastic potential energy in that spring, is equal to my kinetic energy. That's 1/2 kx squared is equal to 1/2 mv squared. And I'm looking for m. I can cancel my halves there, however you want to solve this. But v is going to be the square root of mkx squared. Excuse me. The square root of kx squared divided by m. Okay? And then I would put in the values. This is k, square root of 250. M is 0.02. That's the mass. Squared divided by m. Oh, I'm sorry. No, not 0.02. 0.03 divided by 0.02. That's the mass. And the answer is whatever it is. But that's how you solve those problems. You look at your initial situation, and then your final situation, and then you set them equal to one another. Okay? Christian.
For OpenStax, I was new yesterday. I thought it was pretty easy for the
Most of them are.
Within the last 2 questions, it gave me a 2D momentum problem.
Okay.
It was like really difficult. Are you gonna have a 2D momentum problem?
Not on the test. Right, remember we told you not doing 2D momentum problems. But let me just show you, because it's related. Like we had that one question on on the OpenStax where I had the 2 objects that were traveling like this, and then to solve for that, they were traveling and then they collided and stuck together and move off in the same direction. This is related because you have to do 1D, and it looks the same once you separate it. In this case, we had, I'm going to make the numbers easier, 8 kilograms, 8 meters per second. It was actually like 8.88. Y'all remember that one? Yeah, and this was 7 kilograms, 7 meters per second. And so this will be 15 kilograms, 7 plus 8. And it asked you what was the velocity. So to do that, I would say PIX equals PFX. And then my initial momentum in the x direction is going to be 7 kilograms, that's the velocity, the mass, times negative 7 meters per second. Because this object has an x momentum, but this object only has a y momentum. So I don't include that. And then my PFX is going to be 15 kilograms, because they stick together, times VFX. And I solved that for VFX. So it's going to be negative 49 over 15 is equal to VFX. All right, that would be a 1D problem, right? Just one part of that is a 1D problem. And you'll certainly see 1D collisions on your exam, but not 2D. By the way, on this, if you wanted to go forward, we want to know what VF was. You would do the same for VFY. And you say VFX squared plus VFY squared. Okay? All right. Is that okay, Christian? Yeah. If you want to talk about that particular question, we can talk about it. Mallory, I think somebody was in front of you. Was there somebody else that was waiting? Okay, what was the question? Does she have it up? Can she just show it? It's not easy for me to pull it up. You're off. Isn't she off? Which one is it? Oh, this one. Yeah. So this was the man pushing an object up the crate or up an inclined plane. Now, first of all, this requires you to go back to chapter 4 a bit. I'm not going to make you do that on the test, okay? But you had two amounts of work being done. You had a crate that's pushed up 4 meters. And let me explain, and then I'll explain what not to do on the test. That's not relevant. And it required a force of 500 newtons to go up that 4-meter inclined plane, up the length of 4 meters. And so that work was 200 joules, 2,000 joules, 500 times 4. But then you had a guy that was pushing it, and he had a weight of 850 newtons. And you had to figure out also how much work was required to get him to go up the inclined plane. This angle, and this is the part that's not on the exam, that angle is 20 degrees. And so you know the component of his weight is FW cosine of 90 minus 20, which is 70. And so the work required to make that guy go up would be 850, that's his weight, times cosine 70, times 4 meters. And it comes, I don't know what it comes out to be, but then you just add those two values together. Okay? Blair, was that you that asked that? Is that okay? But you're not going to have to deal with inclined planes in that way. You'll certainly see inclined planes, but you're not going to have to deal with taking components of the force. I'm sorry. Yeah, you could do that. That's clever. It's easier that way, isn't it? Yeah, so another way that you can do this is that if you know the change in height, which you can find, because if I have a 4 meter here, 20 degrees here, and I have then my height, my change in height is going to be 4 sine of 20. Okay? And then you can just say m times g times h. That's whatever the mass of this is. Did they give the mass of that block? Oh, I don't know how you found the mass. I guess you... Oh, that's not right. You can't do it that way. Did you get it right?
Yeah, I got same exact number, 4160. Must have just been
Something. I don't know what it was. Okay, but if you know the mass, then you don't have to worry about the forces. You just say what is the change in potential energy. PE is mgh, and that will also equal to the work that's required to go up that incline. Okay? All right, Mallory.
Oh, I was just asking if there's an easy way to remember like the formula that you use for like inelastic versus elastic collisions.
Well, yes,
I mean, I know it's on the formula sheet. Like, just how do I tell?
they're the same. Really, there's a separate type of the elastic collisions we're not really dealing with. We are dealing with them, sort of, but elastic collisions conserve energy. And so with elastic collisions, the following is true. And we haven't done this, but you might have done it in your Chem 10 something class. We know that PI is equal to PF, and then also in elastic collisions that EI is equal to EF. I mentioned this in class, but we didn't solve this system of equations, but it can be done. So with elastic collisions, you know that these two things are true. With inelastic collisions, only the first thing is true. PI is equal to PF. And so really all that we're doing in that chapter 6 is this first part. In chapter 5, we're dealing with that second part. But we're not doing collisions where energy is conserved. We're just looking at systems where energy is conserved. So the answer to your question is use the same conservation momentum for both types of collision. But I do want you to know the difference between the inelastic and elastic collisions. Inelastic, not conserved, right? N is not. Energy is not conserved. Elastic, energy is conserved. Does that help?
Yeah, my question is more like I know doing some of the like momentum homework. Some of them were like M1 V1 plus M2 V2 equals M1 plus M2 V final, and then some were like V1. Like which situations do I?
So you're asking something a little bit different. So you're always starting with this. That's always your starting point. And then that expands if you have two particles to M1 V1I plus M2 V2I. That's your initial momentum. If you have two particles, if you have three particles, there'd be a third. If you had 1,000 particles, there'd be 1,000 terms. But we just do two. M1 V1F plus M2 V2F. So that's where we're always starting. But sometimes some of these terms go to zero. Like for example, if your initial system is at rest, this whole side goes to zero. Or if something is at rest on the second side, then you'll lose one of those terms. So one or more may be equal to zero. If you have a perfectly inelastic collision, in a perfectly inelastic collision, M1 equals M2. They're equal because they stick together. And so both particles have the same mass. And so it's just a special case of this where, or excuse me, I'm sorry, not M1 equals M2. V1F equals V2F. Because they stick together and they move off at the same speed. And so that's why we say M1 plus M2 equal or times VF. Because both particles have the same speed. But it's really just saying, well, this is equal to this, so I can factor it out. Yeah. Okay? Those problems are actually easier to solve because, you know, you have fewer variables in them. Allie? Can I see? Yeah, this is a 2D problem. Which one? Oh yeah, that's the one I was just working. Yeah, so it does matter, but you will not have to work a 2D collision problem on the test. That's like this problem. I changed the numbers just to make it easier. This one's moving in the negative y direction. That's 270 degrees. This one's moving at 180 degrees, negative x. And then they stick together, and they move off in the same direction at the same speed. And so I just worked part of it. Where I said Pix is equal to Pfx, the x components, and this is the only initial x component, and then you can solve for the x component of the velocity here, which is this minus 49/15. Next question. Question. Yeah. Oh, it's this one, number 8, you said? Okay, so this is another type of elastic potential energy, Rachel, like we asked about before. Right, so here, what's, oh, that's 6. Okay, this is a combination of work energy theorem and conservation of energy. So we have a couple of things going along. I'm going to work a different problem first. I got this kid, he's kind of a boxy kid, and he comes down a slide, and he starts at 3 meters high. And let's just forget about friction for now and ask, what is his speed at the bottom? Well, this is just like we've been doing. We say mgh equals 1/2 mv squared. Remember, no friction at all right now. M's cancel. That's 10 times 3 meters equals 1/2 v squared. And then you solve for that. It's, you know, the speed would be 7 point something. All right? But our speed is actually going to be less. Oh, so we could go ahead and pick it. It's actually going to be b. Right, B's the answer for 8? Yeah, because I know the speed has to be less than 7 point something. Because as this kid slides down the slide, there is a frictional force that takes away energy. And the amount of energy that it takes away is the work done by that frictional force times the distance. The frictional force times the distance. But this is a 5 meter long slide. So for the entire 5 meters, that frictional force is acting, taking away energy from that kid, continually taking away energy and causing him to slow down. And the amount of energy that he takes away is 10 newtons times 5 meters. He takes away 50 joules of energy. Okay, so what we have to do now is we say, well, he started out with mgh. But then we subtract 50 from that, and that's equal to 1/2 mv squared. And now our m's don't cancel, so be careful. It's going to be 10 kilograms times 10 meters per second squared times 3 minus 50 equals 1/2 of 10 v squared. It's 300, that's 250 divided by 5. 50? Is equal to v squared. Square root of 50 is 7, or 7 point. 7 squared is 49, so it's just a little bit more than 7. Okay? It's a good question because it combines conservation of energy and the work energy theorem.
How do you know which side to subtract it?
Because she asked, how do you know which side to subtract the 50 from? This is his initial energy. Like, this is a bigger amount, I know, than this, because this is what he has at first, and this is what he has after going down the slide. And after he's gone down the slide, that's when he's lost all that energy. And so I know I have to subtract the 50 from the bigger number in order to get a smaller number. Next. Now y'all have questions. Claire? Uh-huh. Another good question. You're going to have a collision. It'll be similar to this. It may be perfectly inelastic or just inelastic, but you'll certainly have a collision. On this one, you start with Pi equals Pf. Because it's inelastic, or perfectly inelastic rather, that is, they stick together, I'm only going to have one V term for the final because they're moving off at the same speed. So Pi is 2 times 4 plus 4 times V2 initial. That's what I want to solve for. And by the way, I know this thing has to be going to the left because the final state is moving to the left. So something has to be moving to the left. So I could go and get rid of these guys. And then that's equal to 2 plus 4, which is 6, times negative 5. That's the speed. That's mass times the velocity. So that's 6, negative 30, negative 38, divided by 4 is V2I, B, 9.5 to the left. It's a good example. You'll certainly have collisions on the test. You'll have a couple collisions. In fact, I think I give you one with a picture like this, which I think helps you a lot. But then I also give you one without a picture, where you have to think about the words that I use to describe the collision, and then translate that properly into the equation, and then solve that equation. But y'all can do that. You can. Right? Yes. What's next? And look at some older tests if y'all want. This is fall 12. This is a good question. This is another momentum question. Are y'all tired of momentum? This is interesting because the swimmer is initially on a raft. Nothing's moving. So the initial momentum is equal to 0. And so now I want to know what is the final momentum. This is like the Amy and Gwen problem. Remember they're on the thing and they push apart? Or it's like the cannon where it shoots the cannon and the rail car goes off. So the final momentum is also equal to 0. So you say Pi is equal to Pf. 0 is equal to m1 v1f plus m2 v2f. The left-hand side is 0 because nothing's moving at first. Vi1 and 2 are at 0, so it's equal to 0. So 0 is equal to 75 times 4, that's the speed of the diver, plus 500 times V2F. And you solve for V2F. So that's 300 divided by 500, which is 0.6. Right, this is negative 300 divided by 500 equals V2F. And it's negative because we took this to be positive, and so I know that the speed of the raft is in the opposite direction. You jump off, you go that way, and they go that way.
So like it doesn't velocity is super zero.
Right, yeah, because here is just, they're sitting on the raft, right? Nothing's moving, and then you jump off, yeah. That's momentum. Here's some kinematics, rotation. You want to look at some rotation business? Yeah? That's not a very good one. Let's go to a different one, okay? We'll do some rotation. What? No rotation on that one. Okay, so let's look at number 1. And really at this point with these kinematics questions, it's just being able to read them and pick out the proper quantities and then apply the right equation. But that's not always easy if you're not familiar with them. So here, it's initially at rest. That tells me omega naught. It has that acceleration that tells me alpha, and this is theta. Notice that everything's in radians. Check your units on all of these things, especially in that third section of the exam, which is on rotation. Just check your units. Try to make it clear when the units are especially important, but always be aware of your units. And I'm looking for T. And then remember my equations. You'll have them on your equation sheet, or you can write them down. And ask yourself, oh, and by the way, on the equation sheet, we usually leave this off, but there is a theta naught term there, the initial angle. We always have that equal to 0 because you can set it to whatever you want. And so we've always set that equal to 0. So we never really think about that, but it's on your equation sheet. So just be aware that it's there because that is the full equation. And then think about what you know and what you don't know. And we know then that we can use this equation, omega naught t plus 1/2 alpha t squared, and then solve for t. Fortunately, omega naught is 0, so this term goes away, and we have 16 equals 1/2 of 2t squared. T is 4 seconds. The square root of 16 is 4. Okay? A similar one here in number 2 moves from rest, that's omega naught, to omega final of 8 and a t, and we want to know the acceleration alpha. Notice here everything's in revolutions, but it's in revolutions down here too. Kinematics problems you can work in any unit that you want. That's not true when you're relating angular to linear quantities, and that's not true when you're calculating centripetal acceleration. You have to be in radians for those. So here, if I want to know angular acceleration, I'll say omega equals omega naught plus alpha t. 8 equals 0 plus alpha times 2. So alpha equals 4. One revolution is how many radians? 2 pi, right. Know your unit circle will help you. But if you don't know, just remember 2 pi radians equals 1 revolution equals 360 degrees, because you will have to convert radians, revolutions, and or degrees on the exam tomorrow. But remember, this is 0, pi over 2, pi, 3 pi over 2, and 2 pi. I mean, everybody should know the unit circle anyway, because it's an important thing to know, the unit circle. In fact, the new president, I believe, is going to ask every graduate of Nichols to draw the unit circle before they walk across the stage. Wouldn't that be something? Y'all didn't even think that was funny. Okay. What else? Look at number 10. This is about our centripetal force. Here I have a 1,500 kilogram car, goes around a curve with a radius and at a certain speed, and I want to know the coefficient of friction. Now remember, when you have circular motion, there is some force that is the centripetal force. And in this case, the centripetal force is the static friction. In some cases, it's the tension. In some cases, like the gravitron at the fireman's fair, it's the normal force. But in this case, it's the static friction. So you say Fs is equal to Fc. That is mu times the normal force, which is m times g, is equal to mv squared over r. And then you can take that and solve now for mu, because you have v and you have r, and your m's cancel out, and you can solve that for mu. See, that's it on that test. Everything else is chapter 8. Anything else? Which one? Number 5. What is the angular velocity of the second hand of a clock? Well, a clock hand goes around the full circle, which is 2 pi radians, in how many seconds does it take to go across? How many? Oh, 60, right, because it's a clock. 60 seconds in a minute. And so that's pi over 30, which is roughly 3 over 30, which is 1 over 10, or 0.1. And it would be negative if we were looking at signs. Remember, there's no right-hand rule business, but you do need to know clockwise, counterclockwise is negative or positive. Okay? What else, folks? Y'all feel okay about this? What's our general feeling? I want a good showing on the exam. I want 90% average. 90%. We would have a party. I'll probably cancel class. Probably won't even come to class. How about that? If we have a 90% average, no class. At the end of the semester. Okay? Is that all, y'all? All right, I'll be around for a little bit longer, so if you have some questions, please feel free to drop by.